Hey everyone, in this video we're going to talk about weather forecasting. This is going to be a 10,000 foot view more or less of what weather forecasting is and how meteorologists actually go about doing it. So weather forecasting can really be thought of as half science and half skill, just because we're taking the basic principles of the atmosphere and applying them, but we're also looking at different weather patterns because weather patterns tend to repeat themselves. So we have all of that working with us in order to create a weather forecast. It's not always as easy as it looks. I know that it may seem very straightforward, but in reality, meteorologists are really just trying to predict the future state of the atmosphere. So we are trying to predict the future. And predicting the future is not so straightforward. If I were to ask you, what are you doing in the next hour or so, you probably have a pretty good idea of what you may or may not do. However, for instance, if you were leaving work and you weren't expecting to get into an unfortunate accident or expect to get stuck in traffic, it just happened, well, that was unforeseen. So again, predicting the future isn't as straightforward. If it was, then everybody would be able to accurately guess what the winning lottery numbers are, and everyone would have been rich yesterday. So that's another prime example of why weather forecasting is not always as straightforward as it seems. And there's many important reasons and many different jobs for meteorologists because there are many different entities out there that are reliant on weather. So many of you are very familiar with the newscaster, who is the meteorologist who tells you what the weather is going to be for the next 5 to 7 days. And oftentimes they can get a bad rap because if they're wrong, it makes it seem that they don't know what they're doing. But in reality, the atmosphere is complex and it just becomes very hard to predict at times. And there's also the federal government, the National Weather Service, which is just a branch of NOAA, which is the National Oceanic and Atmospheric Administration. They hire meteorologists, hundreds of meteorologists across a variety of different entities, like their 125 weather forecast offices around the United States and its territories, which would be Puerto Rico and Guam and the American Samoa. But the National Weather Service also have meteorologists in other parts of government, like the Federal Aviation Administration. Those meteorologists provide forecast information for the aviation community. And the main mission of the National Weather Service is really just to provide weather and climate forecasts, warnings such as tornadoes, severe thunderstorm, flash flood, river flood warnings to the United States and its territories, and also to predict offshore weather like offshore wind and offshore wave height, all to protect life and property in the United States. And essentially every main government or every established government has their version of the Weather Service. Like England has the Met Office, that is their federal government version for meteorologists. Now there are private sector meteorologists as well. They also do operational forecasting, like those in the marine community. The marine community can forecast critical weather information for marine operations, whether that's international shipping routes or commercial fleets, or maybe even offshore wind farms, or maybe even recreational boaters to your major cruise lines, fishing boats, things of that nature. They all rely on weather forecasts too. So whether it's a sailboat racing for the World Cup, they can also employ meteorologists because they want to know what the winds are going to be, because that's going to give them a competitive edge. Some major cruise lines like Royal Caribbean also have their own team of meteorologists that they employ so they can give decision support for their operations as well. Aviation, I mentioned just a minute ago. Aviation really just helps the pilots navigate all of the nasty weather in our atmosphere, and makes sense because planes fly in our atmosphere, so they're affected by weather. So aviation meteorologists are really just trying to keep pilots out of areas of severe turbulence and icing, things like thunderstorms and bad weather. And this is all because it's safer to fly in non-hazardous weather. Safer for those on board and also better for the aircraft. So it saves airlines money when your airplane isn't being beat up by turbulence. So aviation meteorologists, they also work for the government. They're called Central Weather Service Units, and they contract directly for the FAA. But there are several airlines that have their own in-house meteorologists, and there are other companies that will forecast for other airlines as well. There's also energy meteorologists. So energy sector meteorologists, they're more long-term forecasting. So they're doing really a week-to-week or a month-to-month, sometimes even during the hours, depending on what different commodity traders are trading. But for example, if you know that the eastern two-thirds of the United States is going to be well below normal for at least a week or so, and you know that the average U.S. home heats their home by natural gas, then you know that there's going to be more of a demand for natural gas than there would be if it was warm outside. I mean, it makes sense because when it gets cold out, people are more incentive to turn their heat on to stay warm. So that means the value of that commodity goes up. So traders want to know this information, so they will also employ meteorologists to do that kind of support for them. So meteorologists can wear a lot of hats, and some meteorologists don't even do forecasting. They do more behind-the-scenes research to operations, meaning to say that they'll create different tools that we operational forecasters can use in the field to make our jobs a little bit easier. So there's a lot of different thoughts and theories about what meteorologists do. We're really just scientists. And so with science, you need data, and you need a lot of data in order to make a decision. And this is how meteorologists essentially make their forecasts. So as a forecaster, me personally, I have to collect, I have to analyze, and I have to look at a bunch of different pieces of observational data. And some of the ways that we get that observational data, one of them being from the National Weather Service in conjunction with the FAA, the Federal Aviation Administration, because they operate over 900 automated weather observation systems, which are known as ASOSs for short, and they give us ground truth on what is actually happening in different parts of the country, and really even the world, outside of the United States. But in the United States, they're called ASOSs. And this is essentially important because we can't be in every single location. I can't be in Boston and knowing what the weather is going on in Chicago if I didn't have data points to go off of, because I can only be in one location at one time. But when you look at things like worldwide, there's over 10,000 land observation systems like ASOSs, about 7,000 ships at sea that collect weather data, hundreds of buoys in our oceans and oil platforms as well. And we also collect weather aloft in our atmosphere, launching weather balloons. And weather balloons are launched across the entire globe twice daily at the same time each and every single day. And these weather balloons contain an instrument called radiosondes. And these are very lightweight instruments, and they are essentially cameras in a sense, because what they're doing is that they're taking measurements, or taking snapshots, if you will, of different weather parameters like temperature, humidity, pressure, wind speed, and direction, and they're taking those observations at multiple levels throughout the atmosphere. And so what happens with all that data that we get from the weather balloons and all the data that we get from the land observations, what happens to it all? Well, all that gets compiled into one, and it gets put into weather models. And our weather models are what we use to help model what the atmosphere may look like in the next several hours, or maybe even the next several days or weeks. So there's a lot of calculus and a lot of physics and a lot of math and science that goes into these weather models. Here are just two equations that basically dictate how our atmosphere performs and why. And I know that this math can seem very, very daunting, and it is. Meteorologists, when they go to school, they have to learn what these equations are and where they come from, how were they created, and what do they actually mean. But in an operational standpoint, you need somebody who's good with computers and programming to basically take those equations and write thousands of lines of code in order to make a weather model, to take data at current time and then project what that data might look like in the next several hours or next several days. For instance, one weather model may take 6 hours to compile, meaning to say that from the time that it starts running all of these different equations, it takes 6 hours to finish. So that's a computer doing math and calculus for 6 hours straight. And that's a lot faster than any human could do it. And they're solving equations that really can't be solved by hand. So this is why supercomputers are very important, and they're also very expensive. And they're calculating all these different parameters for all different levels of the atmosphere. So eventually, once the computer is done doing all of that complex equations, you basically get some type of product, aka you get some type of prediction of what the atmosphere may or may not look like. And because our atmosphere is very chaotic, a small change in the system will really change the entire prediction. So for example, if we get a bad data point from, let's say, a weather balloon, if we get a bad data point and it goes into the model, well, that model might think that that actual piece of data is real. And so what it'll do is it'll change the entirety of the forecast. It's like if a basketball player shot 100 baskets, how many baskets would that player get? Let's say that they shot 70% of all of those, or they made 70% of all the shots that they went to attempt. Well, how come they only made 70%? How come they didn't make the 100%? Right? Because it's small little variations of how you hold the ball, where your elbow is, maybe it was flared out when it should have been tucked in, or vice versa. So all those little changes create a different outcome. It's the same thing in meteorology. So eventually we get a product, as I mentioned before, and these products are what we know as our weather maps. And so there's pictures of the atmosphere, and this is an example of what it looks like. So we can see what is going on in our atmosphere, and all of these different charts mean different things. So forecasters, they use their knowledge and their background, so their experience along with the science, to create a weather forecast. And so there's different types of forecasting, and number one being a persistence forecast. And basically that is when you look at a weather model, and that weather model has come out with numerous different runs, so it's come out with numerous different iterations. And the tendency, meaning to say the forecast, really hasn't changed all that much. So you feel more confident in the forecast over the next several hours or several days because the weather models haven't really changed all that much. It's like when you make plans with a friend or a family member, and then you check in with them a few days before the event and you say, hey, are we still going to lunch on Saturday? And they say, yeah, we're still going to lunch on Saturday. So you feel pretty confident that your plans are going to be like that on Saturday. Now, there's also long-term forecasting, like climatological forecasting, and even just called long-term or analog forecasting in general. And this is looking at climate data or weather statistics over many years or maybe even many months. And it's also based on the fact that weather typically repeats itself. And so this is what forecasters, especially long-term forecasters, will look at, like when they make seasonal forecasts, like what is this year's hurricane season going to look like, or what is this year's winter season going to look like. It's all one big outlook, and it's more of a educated guess because it's very hard to forecast what the exact weather is going to be for the next several months. But basically what we do is we look at what has happened previously, and we kind of compare and contrast what the atmosphere looks like at current compared to what it did years ago. Now, more on a short term, once again, trend forecasting basically just shows the different trends of weather systems over a period of several days or maybe even a week or two. And this is just looking at the different placement of weather fronts or the speed at what they're coming into a region. Is precipitation moving quicker into a certain area, or is it being a little bit delayed? This is what we know as trend forecasting. It helps us give us a probabilistic idea in our minds of what the weather is going to be. And nowcasting is a little bit more of the short term. This is what the weather is going to be really in the next few minutes to maybe even the next few hours, and usually is not based off of any kind of weather modeling per se, but it's usually just based off of what's actually going on, like what's actually going on radar and what the current observations are looking like. So no meteorologist really just sits there and does math by hand, even though when we're in school it can certainly feel that way. So we rely a lot on weather models and observations, a lot of coffee, and yes, we do use social media, because social media, being what it is today, can give us a good idea, especially when it's so easy to take a picture or a video or something and then upload online. We can get a good idea and see what is occurring in different parts of the country, especially when we're not there. So there's different forecasting tools that we use in order to accomplish this. One of them is what we call numerical weather prediction, or NWP for short. Really just a technical name for weather models. And so those weather models are those mathematical models that basically produce a weather map that we use to predict the weather. So there's many different entities that produce these forecast maps. They're called prognostic charts in a very fancy scientific way, but basically that's what we're looking at when we're trying to make a forecast. There's also statistical analysis of these charts, and we can kind of compare that to the accuracy of previous forecasts. And so one model or method that we used to do this, especially years ago, was called MOS, or Model Output statistics. This is an older product, but there's a newer version called the National Blend of Models, or the NBM for short. And they basically look and work the same way. Well, the NBM works a little bit different, but the output is a little bit similar to what MOS was. And this is basically just telling you in a very one-dimensional view of what the weather is going to be in the next several hours to the next several days, using a statistical method instead of more of a modeled method. So some of the weather models that we use in a day-to-day format, really there's three main ones that meteorologists will use daily. And there are others out there, but the first one being the NAM, or the North American model. It's a little bit more of a short-range model. It forecasts 84 hours out, so that's about 3.5 days. And there's a bunch of versions of the NAM because the NAM is built in a particular fashion. And so the NAM has different variations like the HRR, the high resolution rapid refresh, or the 3-kilometer NAM, which is a little bit more of a high resolution version of the original NAM. And so this NAM model runs 4 times a day. The HRR updates every hour. So depending on if it's more high resolution or not, it can run a little bit more frequently throughout the day. Now the GFS, this is a global model, and it stands for the Global Forecasting System. And so it forecasts about 384 hours out, which is roughly 2.5 weeks. And that also runs 4 times a day. Now, the European model, you might have heard of this a lot in the news, especially if you watch the weather on a regular basis. But the ECMWF stands for the European Center for Medium Range Weather Forecasting. That's a lot, so we just say the Euro model for short. And so it's also a medium range model. It's very similar to the GFS, but it's built a little bit different, and it only forecasts out about 1.5 weeks, or 240 hours. And statistically, between the GFS and the European model, statistically the European model has a better track record, as in it has a little bit more accurate forecasts. Now, it only runs twice a day. Now, if you ask yourself, or you're questioning, well, how much better is the European model than the GFS model? Well, if they were both students in school, the GFS would be about have a GPA of about 90, so 90 out of 100, right? 100 being a perfect score. And the Euro basically has an average of about 91.5 or 92. So they're very similar, right? They're both A- students, if you will. And so those are the basic three, and like I said, that there are others. Some of those other models that we use are what we call ensemble models, and this is where we get into a little bit more probabilistic forecasting, especially in the longer term period, like days 4, 5, 6, 7, and beyond. So ensemble forecasting basically takes the same weather model, like the European or the GFS model, and it basically perturbs that model a bunch of different times to create different outcomes. So the code in the weather models are basically changed a little bit, that it produces different outcomes. It's like that scene in Back to the Future where it says, Marty, don't go back and change anything in past, because if you do, when you come back to the future, it's going to be totally different. It's the same reasoning because it's a chaotic system. So ensemble forecasts, they can produce a variety of different outcomes when we look at weather models. And we can plot all of those onto one map, and then we can get a sense of how much error or how much uncertainty there is in the actual forecast. And the further you go out in time, the more chaotic that model becomes. So in essence, this is basically what is an example of a ensemble model. And here you can see where all the different lines are. So if you have lines, especially in the red here across the northern tier of the United States, here you can see that when it is close to the white line here, the white line would kind of be the overall average of all of these different weather models. But you can see that all those individual lines are pretty closely packed together. So there's good confidence on modeling that portion of the jet stream. However, in the purple, in the southern portion of the jet stream, here you can see that those lines are a little bit more spread out. So the uncertainty in those lines is a little bit more chaotic. And here you can see how very chaotic it can be, especially as you go further out in time. Ensemble models are really good, especially when it comes to hurricane forecasting or any kind of big storm like a nor'easter or any kind of big winter storm. When you look at it in terms of hurricane tracking, it's actually pretty good. So here's just an example. This is some tropical storm. This is Erica back in 2015. And here you can see there's pretty good agreement against all these purple lines. Here you can kind of see it goes generally north of the Leeward Islands, goes into the Caribbean, and then once it gets to Florida, there's a little bit of variety here. Some models think that it's going to go into the Gulf of Mexico, kind of hit the Florida Panhandle a little bit, and then others think it's going to just skirt the eastern side of Florida and then go out into the open Atlantic, whereas some models are going right through Hispaniola and Cuba. So there is some variability in this forecast, but the overall trend you can kind of see based off the white line that it's just going to go just north of the Leeward Islands. But in other cases, here you can see that this tropical storm in the Pacific back in 2015, where Hawaii is kind of just smack dab in the middle of all these different solutions, you can see how much more widespread all of these different lines are. So there's a lot more uncertainty in this forecast. So as a meteorologist, if I'm looking at this, I'm really just scratching my head and shrugging my shoulders because I have no idea where this tropical system is going to go, and I'll have to wait a few more days to get some better data. So when do these models actually run? When do they start compiling all of that data? Well, in weather, we have to be on the same time page or the same time scale because we're displaced across the entire globe. Remember, we're launching weather balloons at the same time each and every single day because we're trying to capture the atmosphere all at once. It's like taking a picture. If you were taking a group picture, you would want all of your friends or all of your family members to be in that picture, right? So all together. So we're trying to do that in the atmosphere. We're trying to get a sense of what the atmosphere is doing at a particular time all at once. So we need to be on the same page, which is why we use Universal Coordination Time, or UTC time for short, which is also known as Zulu time or Z time for short. And this is basically based off of Greenwich Mean Time, and Greenwich, England, sits right along the prime meridian, which is 0 degrees longitude, and that means that it's not affected by daylight savings time. So 0 UTC is technically midnight in Greenwich time, just like it would be in military time. 0 o'clock is midnight. 0600 would be 6 a.m. 6Z would be 6 a.m. in Greenwich, England. So we're not in Greenwich, at least if you live on the East Coast. We're several hours behind, either 5 hours or 4 hours, depending if it's daylight savings time or not. So for us, especially on the East Coast, 0Z is technically 7 p.m. the day before. So if it's 0Z on the 1st, then that means it's 7 p.m. on the 31st or the 30th, depending on what month it is. And so that's during daylight savings time, or when it's not daylight savings time, 8 p.m. when it is daylight savings time. So depending on where you are throughout the country, 0Z can be different things. So if you're on the West Coast, if you're in California, 0Z, if it's not daylight savings time, would be 7 p.m. on the East Coast, and that means it would be 4 p.m. on the West Coast. So midnight in Greenwich is 4 p.m. in LA. So we use that to be on the same page in terms of when we're launching weather balloons and we're coordinating data. So the NAM and the GFS, like I mentioned, they run 4 times a day at 0Z, 6Z, 12Z, and 18Z. That would be 7 p.m. on the East Coast local time. And this is not daylight savings, and there would be 6Z would be 1 a.m. our local time, right? That would be 6 a.m. in Greenwich, England. 12Z would be noon time in Greenwich, that is 7 a.m. East Coast time. And 18Z, that would be 1 p.m. East Coast time, or that would also be 6 o'clock in the evening in Greenwich, England. So new data is only inputted into these models at 0Z and 12Z. And the European will only run twice a day. So you might say, well, how come the American models like the NAM and the GFS, they run 4 times a day? Well, they basically use the old data from the 0Z and the 12Z runs, and they kind of just make it work to create 2 different run patterns to kind of be competitive with the European model. So when we start to make a forecast, we like to think of the atmosphere like a giant river, and it really flows like water. And it's a good way to think about because the atmosphere behaves like a fluid. It acts like water when you kind of look at it in real time. And so when we look at the high levels of the atmosphere, like the very upper part of the jet stream, like 200 to 300 millibars, which is like 30 to 40,000 feet above the surface, and we look at that level first, we can kind of work our way down, and the different levels of our atmosphere can tell us different things about the weather forecast. So these maps are, again, the very, very top of the atmosphere, and it basically looks like this in a very artisan drawing, where the darker colors, especially the darker pinks and the reds, indicate faster wind speeds aloft, and these wind speeds can be in excess of 150 miles per hour, or they can be very, very light, depending on what's going on. Here you can see in this picture, you can see a portion of the Midwest going into southern New England. Those wind speeds aloft are very, very fast. But as you go over to the West Coast, you can see how there's really no colors indicated on this map, and you can see that the wind speeds are just very, very light, even at the high levels of the atmosphere. So because our jet stream is a river, it really has two different types of flows. It can either be more of a zonal or a flat flow, or a meridional flow. And basically this is what they look like. So a zonal flow would be flatter, meridional would be a little bit more curved. Here's a better example of a meridional jet. You can just see here the big waves that occur in this example, where we have troughs or dips in the jet stream, in this example over the Pacific Northwest, and then we have a really big ridge over the central portion of the U.S., and then another trough over the eastern U.S., and then another ridge over the North Atlantic. So you can see what happens to one portion of the jet stream really affects the entire wave or the entire river downstream. So the more waviness you have in your jet stream, the more significant weather you're going to have, because you're going to have bigger differences in the overall weather, and Mother Nature likes to be a little bit more even. So that's why we have big weather systems when we have big meridional jets. Here's an example of a zonal jet stream. So this is jet stream, especially over southern Europe. It's still a little bit wavy, but it's not as wavy as this example, right? So it's a little bit flatter. So a flatter jet stream usually indicates a little bit calmer weather, because the atmosphere isn't really experiencing too much drastic changes. So the placement of those troughs and those ridges, where the dips are in the jet stream and where the crests are, if you will, in the jet stream, it says a lot about the weather. So troughs are associated with low pressure. Usually it's cooler weather or cold weather, right? But cold and cool are subjective, right? What some people think is cold, others don't necessarily think it's cold. But any case, a trough is usually associated with more opportunities for unsettled weather, things like clouds to big rainstorms or big snowstorms. Ridges are really the opposite effect. Ridges are associated with high pressure, more sunshine, dry weather, and usually warmer weather. Depending on what time of year and location, it can also indicate hot and humid weather. Here's just an example of what that looks like. Here you can see a big ridge over the western U.S. You can really see that big U in the blue here. That would be the trough that extends all the way down into Texas, even into the Gulf of Mexico. And then you can see another ridge over the eastern seaboard. So over the west coast, it's sunnier and drier. In the trough, it's cooler and more areas for low pressure. And here you can see in the east coast, you can see that we have a ridge, so it's a little bit warmer as well. This is typically what you see when you watch the news. So this is an example of really the previous image that you just saw, but it's a little bit drawn for the non-scientist to understand. Here's just another example of what one would look like. So these jet streams are considered long-waved things, and the scientific name for that is Rossby waves. And because it looks like a giant wave that spans a good chunk, really the entirety of both hemispheres, both the northern hemisphere and the southern hemisphere. And within that entire long wave, or really think of it as a river, right? Because it's essentially one giant river that spans the entire globe. So because we have that river, what affects one portion of the river is going to affect another portion of that river. And if you've ever been whitewater rafting before, you can run your boat all the way down the river, and within that you have rocks underneath in the riverbed, and as the water moves over the rocks, it creates that running rapid. And so those running rapids in our atmosphere are known as short waves. Those short waves are small spirals within the long waves, or within that giant river, that produces our low pressure systems or our weather systems. So here's an example. The image on the left really just shows the entire wave, right, or the entire running rapid example here. And in the right image, you can see the little dips within that long wave is what we call short waves, and those little dips are associated with our low pressure systems. So when we look at where do these waves occur, we like to look at what the atmosphere is doing somewhere in the vicinity of 20-ish thousand feet above the surface of the atmosphere, which is also known as 500 millibars. So it's a really good level to start looking at when you're trying to make a weather forecast, because you can see the outline of the jet stream, but you can also see where all these little ripples are. And so I like to think of it as a good starting point for your forecast. You can kind of think of it as you just scrolling on your favorite social media platform. You're not necessarily looking for anything important. You're just trying to look at something that may catch your eye. And that's what looking at 500 millibars is essentially for meteorologists. We're kind of just looking at where the troughs and the ridges are and who's warmer, who's colder, who's experiencing low pressure, and who's experiencing high pressure. So on a 500 millibar map, you'll notice these different lines, which are called isobars. And they have numbers on them, and the numbers indicate different pressures at 500 millibars. So the higher the number, it means the higher the pressure, and that usually indicates that it is also warmer air as well, because warm air pressure expands. So higher numbers are found in the ridges, while lower numbers are found in the troughs. Here you can see in the bottom left corner here of this map, you can see a 576 isobar across the desert southwest. So here you can see that ridge, and as you can see here on the east coast, you have lower heights. So this would be lower pressure. So here you can see, especially where that circle is in the Canadian Maritimes, you can see that would be an example of where an upper level low pressure system would be. And pressure decreases, especially as temperatures get cooler. So this is just an example of how those numbers essentially work. In this example here, you can see that it would be warmer and drier over the western portion of the United States, and it would be wetter and cooler, especially over New England. So this layer of the atmosphere is decently important because it shows all of these different things, like where the waves are in the jet stream and also where these short waves are. Well, those short waves, they're important because it creates this energy called vorticity. And vorticity is essentially a rotation in a fluid. And vorticity is really just a byproduct of those short waves, and it spawns low pressure systems. And we often call short waves and vorticity the same thing because they really are the same thing. It's really just a rotation of fluid. And that rotation in a fluid is what spawns low pressure systems. So you can think about vorticity or short waves being the parents and low pressure systems being the offspring or being the kids of those parents. Vorticity can be plotted on maps in many different ways. Here's just an example of a National Weather Service forecast map for 500 millibars. Here in this example, you can kind of see an area of low pressure kind of moving through the Pacific Northwest. You can see a little bit of that dip or that U in the jet stream, and over much of the rest of the continental United States, here you can see a giant ridge over much of the central U.S. going all the way down to the south central U.S. near Texas and the Gulf of Mexico. You can see a very, very large ridge that would be indicative of a large area of high pressure, especially warmer weather, even though there is a little bit of a cutoff low near the Gulf of Mexico, Louisiana, Arkansas area, and then we have a little bit of a trough or an upper level low, especially as we go into portions of the North Atlantic. Different websites and different weather maps will look different. Here's just another example where we have a short wave out in the West Coast. We have a little bit more of a ridge out in the central portion of the West Coast, and we also have a trough over the eastern part of the United States. So it really just looks a little bit different. So vorticity can be thought of like your ceiling fan. If you turn your ceiling fan on, it usually has two modes. It usually has a mode where it can pull air upwards, or it can push air down, depending on if it's spinning clockwise or counterclockwise. So vorticity really works in the same fashion. Vorticity can either spin in a positive direction or a negative direction, and it can indicate what our weather is doing. If it's spinning in a positive direction or counterclockwise, in the northern hemisphere at least, if it's spinning counterclockwise, then it forces air to rise, and that causes precipitation. Or if it's spinning clockwise, then it's forcing air downwards, which is causing higher pressure because pressure of air is being pushed down onto the earth, and that causes dry weather. So we refer to the motion of either this positive vorticity or negative vorticity in the term of advection, which just means the movement of something. So we're talking about the movement of air here. So positive vorticity, advection, means that air is rising into a region, which is causing low pressure to move into a certain part of the country, whereas negative vorticity advection would be high pressure moving into an area causing dry weather. Here's just an example of another version of weather models. Here you can see on the left-hand image, this is an example of vorticity. Here is a very, very strong center of vorticity or shortwave circled here in the black. And you notice on the right image, this is the same timestamp. This was 6Z on Wednesday, the 19th of August of 2015. And here you can see that that shortwave basically produced the area of low pressure, where the low pressure center is basically moving its way into Michigan, even though the parent shortwave is kind of back towards the Dakotas in Minnesota. So you can see that the low pressure system is just slightly ahead of the shortwave. And that makes sense because if air is rising and vorticity advection is moving from west to east in this case, then it makes sense that the low pressure system is going to be a little bit further along than the parent shortwave. So upper air flow and weather forecasting, remember that we're looking for trends and we're looking for how the forecast basically evolves over the next several days. So here you can see there's 4 small images in the top part here, and this is for February 1st through February 4th of 2003. And that dashed line, that dashed red line basically indicates where the different troughs are. And those different troughs are associated with low pressure systems. So here you can see where that trough axis is. If you basically cut the trough in half, or if you cut the U basically right down the middle, this is what it looks like. Where to the right of that line is where you can see your area of low pressure forming. And to the left of that line, you can essentially see where your high pressure system is forming. So as you look through time, you can see how that red dashed line basically moves eastward across the several day period. And in the bigger picture down below, you can see what the surface map looked like for the same day, February 4th of 2003. You can see up at the top right, you can see where the trough essentially was. It's basically back through the Great Lakes and extends all the way down to Georgia and Mississippi. But the parent low pressure system is actually moving through northern New England. And so that is representative of what positive vorticity advection is. It's the movement of a low pressure system ahead of the parent trough. So within those short waves, I know this is a lot of information, but within those short waves, it usually dictates what kind of atmosphere that we have. We can either have a barotropic atmosphere, which a barotropic atmosphere is usually just a uniform area of temperature and humidity, usually found in the tropics or usually found in the very polar regions. It's a region of uniform temperature, so there's really no weather fronts, meaning to say that there's really no clashing of air masses, because the clashing of those air masses is essentially what causes our weather, right? And that moves throughout the jet stream as the jet stream moves. So, or you can have a baroclinic atmosphere, which is basically the mixing of 2 different air masses. And so that's when you have your short waves develop. And so within those, you can either have the movement of weather fronts like warm and cold advection. And so what that looks like on a weather map is what follows. So here you can see, here's an example of some kind of trough. Here you can see in the left-hand image in the top, you can see that would be the jet stream. So here you have cold air to the north and warm air to the south. And that little kink in the jet stream basically will continue to form. So now we have air that is converging right before it gets to the very bottom part of that U. So as air has to turn, it basically converges. When air is converging aloft, it has to be pushed down onto the earth. And if it's being pushed down onto the earth, remember that is high pressure because air is being forced downwards. Whereas air that is rising causes low pressure. So this is usually indicative of a warm front, and that is indicative of air rising aloft, which means it has to converge at the surface and then rise upwards. So this is an example of what a low pressure system looks like. In a more real example, this is kind of what it will look like, where you have airflow in the jet stream, and depending on where it is in regards to the trough axis, where that dashed line is, air is either converging or diverging. So air is either sinking or it's rising. If air is sinking, that's high pressure. If it's rising, it's low pressure. So when we look at the different levels of the atmosphere, especially as we get closer to the surface, they can start telling us different things, especially when we look at 800 to 700 millibar maps, which would be anywhere between we'll say 10,000 feet and maybe up to 20,000 feet above the surface of the atmosphere, depending on location and temperature. So these can basically show us where our different air masses are and where our frontal patterns are. So we can see where there is warm air moving into a location and where there's cold air moving into a location. It also outlines the jet stream a little bit, but it can also be a little bit better at identifying where our different weather fronts are. And that's important because that affects weather. And so if we're trying to explain to the public, hey, your most hazardous weather is going to be at this time, it's nice if we can be able to identify that because we're identifying the timing of the movement of these different weather systems. So doing a top-down analysis is very important, starting at the very top of the atmosphere and then working our way down. So 700 millibar maps, at least back in the day, they were really good for kind of being a hybrid between 500 millibars and 850, especially for looking at things like cloud cover or even different frontal patterns. When looking at relative humidity at 700 millibars, anything that was in green would indicate areas where it was a little bit more cloudy compared to areas in the dark brown or gray, which would indicate drier air at 700 millibars, which it would indicate clearer skies as well. 850, that's a little bit better for identifying frontal patterns and also looking at temperature. So there's a couple examples here that I want to show you. The first one being this. This is an image that was on the previous screen, but it's just been blown up a little bit more. And here you can see there's isotherms, or lines of equal temperature, in the dashed red lines. And you can also see that the jet stream is outlined in the black isobars here. And you can see here that there's this low pressure system that is moving through portions of the Midwest. And ahead of that is the warm front, where warm air from the south is moving northward into the continental United States. And cold air that it was originally from the poles is sinking further southward into the continental United States on the backside of the system. This is where these weather fronts basically are drawn. And this is how we know where to draw these weather fronts, because it's just a boundary between different air masses. You can also use 850 millibar temperatures to also indicate what the surface temperature is going to be. So for extreme heat example, this is an example of some very, very hot temperatures out in the desert Southwest during the summer months. So at 850, the temperature at, let's say, 10,000 feet above the surface is right around 30 degrees Celsius, more or less, which is pretty hot. That's around, low to mid 80s, depending on what the exact value is. So at the surface, right, depending on what the lapse rate is and how well air is being mixed throughout the entire layer, that usually translates to temperatures in the 90s to maybe even the 100s. That's a very, very hot and potentially humid, depending on where you are, air mass. For winter months, we can kind of look at where is it freezing at 850 millibars, because that can indicate our areas between rain and snow, or maybe even some mixed precipitation as well. So the layer in the atmosphere between the surface and 850 millibars, that thickness or that layer of the atmosphere is really good for precipitation and kind of figuring out where the precipitation patterns are, if it's rain versus snow, or maybe even some mixed precipitation like ice or sleet. Okay, so it's a little bit better because it's a little bit more of a smaller layer. Satellite and radar weather forecasting. This is usually good for nowcasting. This is really useful when we're looking at radar. So radar is basically showing us where our precipitation is, how heavy it is, different things like that. It can also show us wind velocity, which is good for finding tornadoes. Satellite imagery. We have different modes of satellite imagery, and satellite imagery can basically show us where our different weather patterns are and what things are doing in real time, which is also very useful for nowcasting. It can also be very useful to look at different weather models to see if there's any weather model that is not necessarily capturing what the atmosphere is doing currently. Because if I'm looking at a short-term weather model and it says it should be raining at current and it's not, then I know that that weather model is not behaving correctly, so I'm not necessarily going to pay attention to it, kind of sense. Weather radar works by sending out a pulse and then listening for a response. The more dense the response is, the heavier or the denser the raindrop is. And that can be the difference between pouring rain, or it could also indicate ice in upper levels of the atmosphere. So it can be a variety of different meanings. This is an example of what weather radar looks like across the northeast portion of the United States, where the heavier rain bands in this example are moving through portions of the mid-Atlantic, especially in the yellow and in the oranges. That would indicate heavier amounts of precipitation, where the light blues or maybe the light greens would be light to maybe even moderate rates of precipitation. And satellite, once again, it does a good job at showing you where the clouds are and what's actually going on during the ongoing weather event, if there is one. Visible is really good, but it's only useful when the sun's out, because it's just looking down on what the Earth is looking like. And if there's no sun reflecting off the clouds, then it's really hard to see clouds, especially at night. But we can measure it with temperature, and we can use infrared, which is the same thing. It just looks at the heat signature on clouds. So here's an example of what visible looks like. You can see here's the entirety of the low pressure system, and this is what a infrared image looks like. You can see that the darker the colors here indicate the colder cloud tops, and colder cloud tops are usually just indications of colder portions of the atmosphere rising higher up in the atmosphere. So it's just an indication of heavier rates of precipitation. There's also water vapor imagery as well, and this is used to look at the presence of water vapor and movement of different weather systems within the atmosphere. Very similar to how satellites work, but just in a different type of view. So this is the different aspects of weather forecasting. I hope that you found this useful.